using the two operation weight and the signal weight is a decrease the value and the signal is a increase the value. In case of binary semaphore, weight S means set as 0. Okay? Weight is set as 1. 1 means it's used. And the signal is when you exit, release, so decrement. It's a plus. Plus 1 is 0 is locked and the 1 is unlocked. Okay? So using this one, we can use the semaphore for the critical section. Yes?
What's the most popular way to do this?
Most popular way to use?
Yes.
Use the semaphore. What was it?
Well, I mean, not just semaphore, because like Peterson's and
Which solution is the most popular? We will see eventually. Okay? We will see. His question is which solution is the most popular in where the operating system or application. We will see such an example. How we can use. Okay, so which means for the semaphore, so we can use the semaphore as the key at the lock and the unlock. The weight and signal, lock and unlock. The weight is the minus value and the signal is the plus value. But as we discussed before, this may cause the BG waiting. Sometimes it's called the spin lock. Okay, so infinity, the running. Okay, so this is a kind of the example how we can use in the real application. So using the binary semaphore, which means a mutex lock. So who provides such a mutex lock, binary semaphore, operating system? So which means if your operating system provides such a the synchronization solution, this will be provided by as a data structure of the operating system. Okay, or you can use the system library. So system library you can. So for example, here. So you can, this is a thread programming. So there is a semaphore weight. Semaphore weight is the weight operation. So once you define the semaphore, like the semaphore init, okay, it's a mutex lock 0 or 1, okay, and whenever, so in this case, this is a threading programming, sorting, for sorting. So the process will be created, thread will be created. So that may cause the synchronization problem. So to address that problem, like the random function, sorting function, print array, random function, the sorting function, the print array, when they each thread access run the thread function, this will be entry section, and this will be exit section. It's nothing but wait and signal, getting the lock and release the lock. This is one of the examples used by application program. So in the application program, in your program, if you need to handle the synchronization problem, you can use the system library provided by the operating system. So this is one of the examples using binary semaphore. Okay. It still has a busy waiting. So there is another data structure that include the semaphore. Okay, there is a block. So this one is a data structure of the semaphore. So we have the integer value, how many processors it has. Okay, the semaphore itself is the array. So there is no indication about such a value. It's you need to add something additional, the operation to check how many processors are waiting. So, but this structure, in addition to the semaphore, the process list, which means it's an integer value, it has the value, how many of them. Then just like the semaphore, it has the block and wait curve. Okay, so this one is a kind of extension of the semaphore, so the data structure. So how it works? So the wait is based on the block. So we can wait is if we try to enter the critical section, wait, I add that process in the queue using the block. And if the process leave the critical section, wake up, that means remove the process list from the waiting queue. It's based on add the process list. We are going to use the process list as a queue structure. Okay, so then we can through the critical section. So it looks like always we can wait and signal. So which means whenever we enter the critical section, wait and signal. In your programming, like for example, here, wait and signal. Wait, the name is different, but it's a signal. Wait and signal. Always you need to use wait and signal before and after critical section. What if, for example, you forgot this? It's always locked. That causes the mutex lock problem. So first, all the application and operating system, they define the solution of the synchronization problem. But developers should put the wait and the signal before and after critical section. In case forgot, exit. Okay? That is caused the problem. That is mutex lock. Because of that, the old operating system have a lot of such a mutex lock problem. So also another issue is there's a two variable shared data, two variable, and this one doesn't have to be next to each other. Shared data 1, shared data 2. So wait by the process 1, and this one is wait by the process 2. Okay. Then this process 1 need S2, shared data 2. This one need S1. They are waiting each other. Okay? So he holds his laptop, I'm holding my laptop, but I need his laptop for the communication. But he needs my laptop for his testing. Until when? Forever or fighting each other and winner takes all. So it's a called deadlock situation. So deadlock is really a problem in any computer system because how many processes are running on the operating system? Many processes. And how many resources? So a lot of them are shared data. So always it happens. Synchronization problem is different from the deadlock. Okay, deadlock is a stop. There might be no problem, but it's a problem. It's not a progress to the next instruction. So we will discuss this problem in the chapter 7 detail. However, what will be the solution of the operating system to handle the deadlock? Think about he's waiting my laptop, I'm waiting his laptop. One solution is either of them give up.
Timeout.
Okay? Timeout? Yes. Then the certain time, the one of them will stop. Or fighting and the winner takes all, or kill both of them. Okay, but mostly operating system ignore deadlock. Okay? Because of that, if something stops, so that I'm not sure whether deadlock or not is stopped, then what's the solution? Control C. You Control C a lot. So Control C is the user interrupt signal. You can interrupt the CPU. So because of that, you Control C a lot. What happened? Operating system. Why operating system does not care the deadlock? Deadlock is very, very hard to detect and very, very expensive to handle. Because of that, operating system just like that. For example, if I have a 70 student, how many different relationships in this room? So many. It's probably the 70 combination of 2 and 3, and it will be huge number of. So do I need to take care in the classroom? So very, very. If this is the kindergarten, the kindergarten teacher may take care of such a relationship, but too many students, too many different relationships. So instructor in the classroom does not care. Okay, you are in charge of. You are responsible for your relationship, social relationship. Okay, in case something happen, just as your responsibility. So same thing in the operating system. Operating system actually ignore such a deadlock. That doesn't mean it's ignorable, but instead the user application is in charge of to take care of the deadlock situation. So this one is the same thing. The semapro, using the semapro, we may encounter problem of the deadlock. So there are solutions we will see in the chapter 7. One of the solutions, by the way, is the priority. So, for example, who is more important? He is more important because he is serious on the grading, so he needs to take. So his priority is 0, my priority is 15. So in the priority, lower number is usually higher priority. So he has a higher priority, he will continue. Okay, that's the one solution. So usually priority-based, any kind of priority-based solution has the problem of what? Starvation. Lower priority will not get the chance, right? So if my priority always is 15, that happened long time before. Do you remember the history of the Unix system that I showed the several weeks ago? What year is the starting of the Unix operating system? Starting year of the operating system, anyone who remember? 1969 is my year of birth. So it's 1970. 1970 usually we are saying that it's the starting, first year of the operating system. Because of that, if you turn off your laptop, then turn it on without power. So your battery is removed. Still, when you turn on, your date and time is correct. Why? What happened? There is another battery inside. What if that battery is also gone? Then you need to replace it. And sometimes that operating system, starting from when you replace the motherboard, the battery, it starts 1970 January 1st, 0000. So that, because of that, you may not see the older than that. Most of operating system. So the earliest date and time is 1970 January 1st, 0000. Okay. Then one of the Unix system running, I think the Berkeley, UC Berkeley, they keep running the operating system to see how much reliable and so on. And 15-20 years later, they found one process is running for longer than the 20 years. So almost early 1970. The reason is that they realized that the priority is very, very lowest priority, never get the chance to use the CPU. Okay? So you need to address that one, any priority-based approach. So using one of them is the promoting based on the time. And certain time, promote the level and so on. We will discuss more about the deadlock situation later. Okay, so then how we can use such a synchronization solution. Okay, we understand what is a synchronization problem and what is a requirement, how to solve that, the solution of such a synchronization. So instead of the specific case, as I mentioned before, the computer science, they try to model the situation. So there are many, many different applications. We cannot take care of each and every case, okay, to apply the synchronization solution. Instead, we are going to model. Okay, model means kind of standard. If you are taking the database course, we talk about the model, data modeling, database modeling, something modeling. Model means kind of standardization. Then find the rule. So if we the model, the computer science application, we can define some of the very useful and popular model. One is the bounded buffer problem. We already saw the bounded buffer problem. Producer and consumer. We have shared the data like the queue. Okay? Then the producer always create the data and put data inside the queue. Then consumer always read the data. That kind of model is used a lot, like the client and server. Server is always receive the request, and the client and send the request. Then we can define such an application as the bounded buffer problem. Another one is a readers and writers problem. Readers always read the shared data. Always read, just read. It's not a big problem in terms of locking, in terms of synchronization. Why? It's just reading. However, there are processes who are writing the data. How many processes can write the data at the same time? Only one. Should be exclusive. So that is defined as readers and writers problem. This one will be used for a lot of the file operation or even the shared data and also database. They use a lot of this kind of model. And third one is dining philosopher problem. Dining philosopher problem is, I found one video that
of dining philosophers problem. 5 philosophers gathered for dinner.
It's
They
an Indian
sit
accent,
at
right?
a round table with their bowls of rice. A philosopher can either think or eat. For eating, a philosopher must have 2
So-
chopsticks in their hand.
only one,
The problem
as you
is,
know, that we need the
though
2
there are
chopsticks,
5
right?
bowls of
Here.
rice
But
for
only
each
one
philosopher,
chopstick for each
the
person.
chopsticks
Philosopher
are
is a
placed
process.
between
Process,
each
what
pair of
process is
adjacent
doing is
philosopher.
either thinking or eating.
As you can
Okay,
see,
thinking means nothing.
this philosopher
And the eating is
picks
the
up 2
eat the food.
chopsticks
It's a
and
shared
has
data.
a
5
bowl of
shared
rice.
data in front of them.
After
But
he is
using
done
the
eating, he
the
has to
it's not
take
actually
back
shared data. It's
the
for each
chopsticks
process.
in
But
his
shared
plate
data is a
and continue to
chopstick.
think.
So you need to use
Let
both
us
the left hand
see
side,
how
right hand side to
better
eat.
is possible
But the
to
next
eat.
process may need
Each
this one.
philosopher
So
will
it's
pick
a
up
kind
one
of conflict.
chopstick
It's a
that is
synchronization
adjacent
problem.
to him. In this case, every philosopher will have
What is
one
the
chopstick
easiest
in
solution?
their hand and will be waiting for the second chopstick. Because
What is
a
the easiest
philosopher will
solution?
need 2 chopsticks to eat his bowl of
Raise
rice.
your hand.
So every
Those who
philosopher
raise your
will
hand the
have one
first time.
chopstick in their hand and will
Okay,
be
then
waiting
stop.
for
You
the
cannot
another
touch the chopstick.
that
Then
is
that
held by
process
another
the philosopher can eat.
So this is
Okay.
the deadlock
Then
condition.
if the philosopher is done,
Everybody
the
is
next.
having one
Something like
resource
that.
and is
It's a
waiting
lock,
for another
global lock.
philosopher
You can
to
lock
use
the all the table. That's the one
This is an
solution.
example of
Okay. Problem. Only you have 5 chopsticks, but only one philosopher can eat. Utilization is very low. Maximum 2 philosophers can
I
eat
was
the
always
same
really
time.
interested in technology as a kid. When I got to college, I didn't.
My name is Scott, and after studying
Okay, so dining philosopher. So I'm going to quickly skip the solution how to use the semaphore mutex lock. So we can consider the different types of the semaphore, like the mutex lock is a 0 or 1. That will be used for locking. Okay, when and the shared data like the n buffer is accessed, you can get the mutex lock. And the full and the empty is a semaphore. This is a mutex 0 or 1. This is the value. How many? So buffer is not the unlimited. It's a limited. It's a full or empty. We will check the full or empty using the semaphore. It's getting the lock, mutex, and release the lock. At that time, we need to change the value of empty, value of the full. So that is the solution. Okay. Readers writers problem is different from the bounded the previous bounded buffer problem, because there are 2 types of the process. One process is read. Read is not a big problem. However, read is also lock. When you read the data, it's called the shared lock. Okay. So we will define such a read count. Okay. And then the semaphore, when we write the data, that should be exclusive. So we will use the mutex for the locking. So solution is like for the writer. There are 2 types of process for the writing. Writing is you need to get the mutex lock for the writing, wait, and the release when the process is done. The reader's process is slightly different. You need to check how many processes are waiting. The reason is that in case the writer is writing the data, you need to check this kind of value. Because of that, so when you read the data and the signal and wave, it's a signal, the weight and the signal is not for the critical section, it's for the updating the how many, the data, how many processes, read and count. This weight and the signal is not for the critical section, this is for to update the read count. Okay, don't be confused. So some of the students ask why is not weight signal? This signal is for this. Okay, and this weight is for this signal. Okay, because during the critical section, actually it's not critical section. Okay, so it's just read. You can read any time, but you need to check the number of processes who are reading. For what? In case the writer would like to change the value, you need to check how many of them are right. Okay. So that is the readers and write. Dining philosopher problem. So we can define the chopstick for each chopstick as a semicolon. So whether this chopstick is used or not, this chopstick is used or not, this one. So always one solution is you can take the left hand side. If the left hand side is available, then get the log for the right hand side, and so on. Okay, you can get the log, the left hand side, then followed by the right hand side. Problem? It may be that at the same time all process get the log left hand side, then it will be deadlock. So it doesn't satisfy with the the requirement, the second requirement, the progress. Okay, so that is this one. So another solution is you can get the global log, like only one time, at a certain time only one philosopher, one process can eat the rice, which means access the data. So to do that, you can define one more, the weight and this. This is okay in terms of this one. The problem is it has the very limited. So among the 5, the chopstick, only 2 of them can be used. The other 3 cannot be used. So it's low utilization. Okay. So to address that, nowadays we have the new, it's not new operating system, but relatively new data structure. It's called the monitor. Monitor is we want to know how many processes are waiting, who are doing the. So for example, when we have the shared data, who is waiting and who are accessing whether this one is live. So if we implement if we need to solve the critical section problem, we need to code all of this. It's complicated. So we put all this kind of the functionality into the new data structure that is called the monitor. Monitor is kind of the class level, high level of the data structure to solve the critical section problem. That includes the list of the process who are waiting. Okay, so in the diagram like the entry queue. So we have this one manages not only the shared data and the operation, but it also has manage the number of process who are waiting. Then whether that process has a problem, like check the condition. All of these are managed by monitor. So you don't have to worry about whether the entry section and exit section. Instead, you can just, because of that. So far, have you ever realized the synchronization problem? Even though you are creating thread? Probably not, because internally in the program language, they are using the monitor data structure to address the synchronization problem. So I'm going to skip you can use the monitor to solve the dining philosopher problem. Okay? So you can easily understand how it works. Okay, then what about the real solution in the operating system? Each operating system provides their own. So like the mutex, the data structure, or monitor data structure, so you can use such a data structure to in case of the synchronization solution. However, nowadays, even the application program level, you may have the very specific the issue or the problem of such a race condition. So you should be able to, in case the monitor or such a given the data structure cannot solve the synchronization problem, you can manually code like the previous one. You can manually code or manually use a semaphore to address the synchronization problem. So, okay. That's the end of chapter 5. Before we start the chapter 6, let's have the quiz for the chapter 5. Why don't you be ready?